Okay, so we are live. Let's wait for some comments in the chat to make sure everything is right. If you're in the chat already, can you let us know? Can you hear me and James well?
I can do a test. Phrase. I don't know.
Well, no one's typing in the chat, even though I see viewers here. I'm just gonna turn on the sound here. Hopefully, it doesn't echo. Well, no one's typing in the chat, even though I see viewers here. I'm just gonna turn on the sound here. Hopefully, it doesn't echo. Well, no one's typing in. Okay, so I think it's fine. If maybe can you just quickly do a test run there? Okay, so
Yeah,
I think it's fine.
say something.
Yeah. Maybe I'll cut this part. I'll edit this part out.
Say something.
Yeah. Okay, so perfect. I can hear you. I can hear me. So let's just jump into it. So hello everyone. Welcome back to the live stream that I will be doing every Sunday after I release my new video to answer questions or elaborate on topics. Today we have a special guest, James Lambert. James Lambert is another PhD student in my research group, actually. He's specifically interested in how quantum correlations can be used to classify condensed matter phases. And he tends to use entanglement a lot in his research, so I thought he'd be a fun guest to have on today. So James, why don't you introduce yourself?
Yeah, thanks for having me on. Big fan of the show. So yeah, my name is James. I'm a PhD student. I'm just finishing my PhD this year, and as John said, my interest is really in the role that entanglement, and I want to say even more broadly than entanglement, and maybe we can tuck into this a little bit later in the chat. Quantum correlations can be used to understand how matter organizes itself at low temperature, and that's sort of my the main thrust of my research. And I do that work with Dr. Eric Sorensen, also John's supervisor, and yeah, that's me.
So can you elaborate a little bit on these sort of low temperature phases?
Sure. So, I think that most people are familiar with this concept that, I take ice from outside in the wintertime, I bring it indoors, it'll melt into a liquid, and then I put it on my stovetop and I can boil it into steam. And what we understand is happening here is that the sort of structure of the water is fundamentally rearranging itself in response to temperature.
Okay.
And as you sort of mentioned in your videos, a classical way of understanding temperature is in terms of the sort of amount of kinetic energy that's sitting in the system. So I put more kinetic energy into the system begins to fluctuate, and those fluctuations lead the system to assume new arrangements, new forms. And with the example of water, we notice that as the temperature gets lower and lower, the amount of organization increases. So in steam, the water molecules in steam barely even notice one another. Steam is sort of, the molecules are they've got so much energy, they're kind of doing their own thing, they're flying all over the place. I cool steam down, I get water, and water is so cohesive that it actually has surface tension. An insect can crawl across the surface of water because the molecules in the water are sort of sufficiently correlated. And if I cool that down even further, I'll get a solid. I'll get ice, and ice arranges itself into, I think as of now, the count is at least 11 distinct crystalline phases for ice.
Oh, wow.
So there are all kinds of ways that molecules can arrange themselves. So the kinds of matter that I'm really interested in are kinds of matter where, when we cool ourselves down to these very low temperatures, and when all of the degrees of freedom are relatively still, the effects of quantum mechanics become really evident. Okay. So a key example of this is superconductors. Superconductors really emerge fundamentally out of quantum mechanical effects.
Okay.
So when I cool down an insulator, sometimes, it's interesting that superconductors don't necessarily have to be conductive at room temperature. This is kind of a curious fact about superconductors. But in a superconductor, if I cool down the material to a sufficiently low temperature, the electrons in the material can pair up with one another, through a mechanism called Cooper pairing. This is in a conventional superconductor. There are non-conventional superconductors that transcend this fact. And because they've paired up with one another, they become effectively bosonic degrees of freedom. So in physics, there are fermionic particles and bosonic particles. And the difference is really the difference between tennis balls and light. If I have a box and I try to fill the box with tennis balls, eventually the box will get full. I can't stack a tennis ball inside another tennis ball. That's like what a fermion is. And a boson is like light. If I take that same box and I say to you, well, fill the box with light, it's like, what does that even mean? I could shine as many flashlights as I want into the box is never going to get full. So when the electrons pair up in this way, they can sort of collapse and form this cohesive state, this cohesive wave function that superconducts, and that's where superconductivity fundamentally comes from. So that's one kind of quantum phase of matter. My research in particular pertains to magnetic phases of matter. So when you cool down insulating materials that don't superconduct, sometimes what will happen is that the electronic degrees of freedom will form very complex patterns of magnetization.
Yep.
And because in quantum mechanics we can have superposition, these patterns of magnetization can have strong quantum mechanical effects.
Yep.
And that's really what we mean when we talk about low temperature quantum phases. Are these phases where quantum mechanics is the operant theory for how the material fluctuates and organizes.
Yeah, so that's really fascinating. Could you perhaps elaborate how sort of entanglement plays a role here, or or how quantum correlations, classical correlations like that clash? Like, what's the difference?
Sure.
And how that sort of fits into the conversation that you're interested in having.
So this is kind of something that I think is still being understood and explored. It's a sort of very active area of research, and I guess the first thing to say is that there are two features in quantum mechanics which mean that we can't use classical probability theory, right? So in the 19th century, people came up with classical stat mech, and they came up with classical stat mech to sort of bridge the gap between classical mechanics and thermodynamics.
Yeah.
So maybe I'm imagining a system like a gas. Gases tend to be pretty, in this context, pretty classical, a balloon filled with helium or something, where the particles are not interacting particularly strongly with one another. And even if they are interacting with one another, the effects of quantum mechanics are kind of negligible, maybe because of the length scale of the particles or something.
Yeah.
So in quantum mechanics, we have the principle of superposition, right? We have the fact that fundamentally the physics is driven by wave mechanics. And so states can live in superpositions of two different states. I can be a 1, I can be a 0, I can be any superposition of 1 and 0. And the other fact is the Heisenberg uncertainty principle. So when I make a measurement of a quantum system, there are certain pairs of variables or certain sets of variables which I cannot simultaneously determine to arbitrary precision. And so the most famous example of this is the fact that I can't measure the position and the momentum of a particle simultaneously to infinite precision.
Yep.
Okay, so these two facts conspire to sort of break classical probability theory. We need a new theory of probability to make predictions about quantum mechanical systems. And at bare minimum, that really is what quantum mechanics is. It's this sort of probability theory that contains, as a special case, classical mechanics.
Absolutely.
And that's really what I mean when I say quantum correlations. I mean correlations and fluctuations that are emerging in systems precisely because of these two quantum mechanical components.
Okay.
That's sort of what I would say the difference is.
Okay, so that's really fascinating. And then so how does entanglement sort of play a role in how you classify phases?
Right. So the thing with entanglement, right, is that it has a sort of very clear formal definition, which is basically I have a state. Okay, so maybe a quick mention to those viewers not so familiar with quantum mechanics. The setup in quantum mechanics is that I have states and I have one of the setups in quantum mechanics. One way you can do quantum mechanics is I have states and I have operators. Yeah. So the operators correspond to measurements that I make, and the states correspond to how the system is sort of arranged. And entanglement is what happens when I have a system, maybe you say a system of two particles, and the state that describes that system of two particles cannot be represented as a product of a state for particle A and a state for particle B.
Yeah.
The whole is sort of more than the sum of its parts. That's what entanglement is.
Yeah, we sort of briefly mentioned that in the video, but I definitely appreciate the elaboration.
Yeah, so you need to take a running start at this question, right? Because as you mentioned in the video, I can do this business with von Neumann entropy where I can sort of partition out, right? I can say, well, let me just look at, the entropy for a pure state is 0. Let me look at the entropy on a subsystem. And in the context of condensed matter, the way that we use, one of the most prevalent ways that we use entanglement to classify phases is we look at how the amount of entropy on the subsystem scales as I grow that subsystem.
Yep.
So I'm in a ground state, I take a subsystem, I scale up, and as your viewers probably are aware, usually what we would expect in a condensed matter system at 0 temperature or low temperature is an area law. And that fundamentally comes from the fact that the interactions in a material are short-ranged. And so the sort of number of bonds that I'm breaking scales like the boundary of the subsystem that I've taken. Okay.
So just a quick note for everyone. So in a condensed matter system, you expect ground states to obey an area law, and that's usually coupled with a gap from the ground state to the next excited state. For the rest of the spectrum, you would expect volume laws as we derived in the video.
Yeah, that's an important point to mention. Is that it's kind of interesting that the ETH community and as you sort of mentioned to me in some of our discussions about this before, the ETH community and the condensed matter community are interested in complementary parts of the spectrum to some extent.
Yeah.
When we're interested in these ground state correlations, we tend to be interested in these very low temperature states of matter. And yeah, like you say, when the correlations are short ranged or when the interactions are short ranged, when the entanglement is short ranged, we get sort of area laws.
Yeah.
So one of the ways that entanglement can be used to classify a system is there are all these states of matter that obey a sort of extension of the classical understanding of phase transitions. So the classical understanding of phase transitions, let's take our example of water. I start out with steam, and steam has certain symmetries to it, right? It's got translation invariance, it's got rotation invariance. If I'm sitting in a balloon of steam, no matter which way I look, no matter which way I rotate, the steam looks the same.
Yeah. I
cool steam down, I get water, and I cool water down. And water has the same symmetries, rotational symmetries, translational symmetries. I cool water down, water freezes, I get ice. Now, the thing with ice is that ice does not have continuous translation symmetry. The whole point of a crystal is that it has a discrete translation symmetry.
Yes.
So the classical way of understanding phase transitions is I've got a symmetry group that describes my system. At sufficiently low temperatures, I break that symmetry, and that's how I understand phases of matter. In the 1980s, I want to say, 70s, 80s, people began to understand that there were many phases of matter that don't obey that. They don't work in that way. And these phases of matter are what we call topological phases. So these phases of matter don't have a local order parameter. They don't have a sort of local obvious pattern of magnetization. These are phases that are characterized by a kind of global topological property. And it turns out that when you look at the scaling of the von Neumann entropy on a subsystem in a phase that has a topologically non-trivial arrangement, there is a sub-leading correction. You get your area law first and foremost, but then you get a negative term, and sort of denoted sometimes, I'm going to call this term gamma for our purposes. People sometimes, topological entanglement entropy, gamma. This term, in some sense, characterizes the topology of the phase that you're looking at. Mm-hmm. And the fact that it's negative is very important, right? So, your viewers will know that entropy can't be negative.
Yep.
So if I have a leading order area law and a sub-leading negative contribution called topological entanglement entropy, in order for the entropy to always be 0 or greater than 0, I know that I always have to have some non-zero amount of entanglement entropy on the subsystem to counter out the topological term. And this is invariant. It doesn't matter how, the whole point is that it doesn't matter how I choose my subsystem. It doesn't matter how I shape my subsystem. And so this is an example of how we can use entanglement to understand these topological phases of matter sort of beyond the standard paradigm of phase transitions and phases.
Yeah, well, that's very fascinating. And for interested listeners, either right now or in the future, James and I will be making a video dedicated to these topics specifically to sort of give you a very nice introduction with sort of supporting math and pictures and plots and maybe simulations of some kind. So definitely stay tuned for that. And if you're watching now or later, leave us a comment on this video and tell us what you want to see. So just moving on, it's kind of fun to sort of pick the brain of people and sort of see see their story, see the world through their eyes. So I don't think I've ever specifically, maybe I have, I don't remember, but it'd be nice for people to hear. So what made you want to be a physicist or a theoretical physicist? Was there some type of, phase transition moment where you went from, wanting to be a firefighter or something to being a physicist, or like, what's the story of James coming into his love for physics?
I think I'm very typical of people who study physics in that, or at least, yeah, that's my sort of perception. Insofar as I just like learning. I love science. But I also love philosophy. I love art. I love looking at paintings and reading novels and many things that I enjoy doing. And I think learning is just a great joy. And I guess my feeling when I was young was that, I could go to art galleries, I could read novels, I could do all of that stuff and kind of get what I wanted to get out of it on my own. But to understand what was going on in physics really required just sort of years of focused study, and I want to emphasize here quickly that I'm certainly not saying that, making art doesn't require years of focused study. Making art certainly does, but appreciating art is sort of, human beings appreciate art intuitively. One can enjoy a painting whether one's educated in it or not. But if you want to understand what the Schrodinger equation is saying, you've got to do a lot of math and sort of background before you can get to appreciate that. And so sort of amongst many interests, physics kind of won out as the thing that I felt needed, many years of study to really get the level of appreciation from it that I wanted. And that was kind of how I fell into doing physics specifically.
Oh, well, that's really fascinating. So with a sort of general love of physics and mathematics, how did you land in condensed matter physics? Like, what's exciting about sort of ground state physics or low temperature physics in materials that sort of catches your eye?
I think basically every area of physics is super cool. I probably would have been happy doing just about anything. I suppose it was kind of opportunity. McMaster was there. It was nearby. You know what? The honest to God story is I was doing these applications, right? And they're like $100 a pop. And I was like, okay, I'm gonna get like, a couple shots at this. Like, let's apply to a place where, I really feel like I'm going to be comfortable living, and, it's going to make a lot of sense for me to sort of work there. And so I kind of fell into McMaster from that perspective. Condensed matter was something that as an undergrad, it probably, I would say, wasn't my favorite area of physics. As an undergrad. Yeah. I mean, I think when you show up in undergrad, you're really hyped up on cosmology and particle physics. There's a sort of great popular science community out there. And I had read A Brief History of Time and these books by Michio Kaku Physics of the Impossible, for example.
I was definitely the same. I think almost everyone you meet is the same. That's
absolutely
as you know, like that's why this channel exists. Once a week, I'm gonna update people and try to get them excited about things in condensed matter physics and statistical mechanics. So that
I think that's wonderful, because it is this sort of, it's a little bit of there's something a bit tragic about it, right? Because on the one hand, it's wonderful that so many people have been able to experience the wonders of physics through the eyes of particle physicists and astronomers. Yeah. But really, that's just the tip of the iceberg. There's so much more physics out there beyond that. And I certainly didn't know about a lot of that physics when I showed up in my first year of my undergrad. So, yeah, I think, condensed matter was one amongst many areas that I was interested in. I actually did my undergraduate thesis in cold atom physics, cold atom physics theory project.
Okay.
And I think cold atom physics also is extremely fascinating. And I did a summer research project in a biophysics lab working on optical coherence tomography. So there were a couple of different areas where I felt like I probably could have gone and enjoyed my research. But it's a bit hard. It's a bit of a tricky question to answer, because in explaining why I'm in condensed matter, I think it's more accidental than anything else. I don't know if it was so planned. It was sort of something that I fell into, I suppose.
Yeah, I think that story is actually pretty common. I had no idea really that foundations of StatMech was really a field at all. It was sort of a spur of the moment thing after I took thermodynamics and quantum mechanics. So I was like, wow, I just wish you could just do both those things at the same time.
It's surprising to hear you say that, John, because, knowing you as I do, you're such a fan of ETH and so passionate about it. It's fascinating to imagine a time when you didn't think about ETH all the time.
Yeah, it was a life-defining moment when I went to go talk to Marcus Mueller, my first supervisor, and he was going to give me. And but by the way, I see the question in the chat. We're definitely going to get to that right once this sort of winds down. But yeah, this was like, I was like, do you have a potential project for me? And this is the first thing he pitched me, and it's sort of like a, perhaps that's cliche. Perhaps I should have listened to more project ideas. But this is basically the first. It was my first exposure to an active research topic. So Guitar Man says, what realm of physics gets left out because there's no good pop sci out there for it? And I think the strange thing is that so there's a lot of pop sci for black hole physics and cosmology, astrophysics, astronomy, all that stuff. And certainly there's probably some stuff out there for things like superconductors and stuff like that. But condensed matter physics as an entire community is absolutely gigantic. I can't cite the actual proportion of publications that come out or like active researchers, but it is the majority of researchers. And you can imagine that inside that field, there's, in this huge umbrella field of condensed matter physics, there is a lot of really exciting things going on right now, right? With very counterintuitive results or very exciting results that, might affect the way we think about physics in the future or something like this. I don't know, James, if you have...
Yeah, I feel like in answering the question, I'm actually going to maybe refute myself. Can I mention, we've already talked about a couple of book titles. Can I recommend a book title? Is that allowed on the live stream?
Absolutely. If you send me a link to where the book can be found, I'll post it in the comments section after.
Okay, swell. So there are two pieces of reading that I would encourage if people are interested in understanding. So I want to answer Guitar Man 14141's question in two parts here. So the first thing I want to do is recommend two pieces of reading. So the first one is A Different Universe, written by Philip Anderson. Philip Anderson is a Nobel laureate, and
is that the Anderson?
That is the Anderson. So a lot of people don't know this, but
so, by the way, spoilers. We're going to do a video on Anderson localization in a week.
Oh, that's swell. That's wonderful. Yeah. So Anderson, is an interesting character because the Higgs mechanism. So a lot of people maybe will have heard of the Higgs boson, and what people might not be aware of is that the science of the Higgs mechanism was actually pioneered in the context of condensed matter physics by Philip Warren Anderson and by others. Anderson wrote a paper called More is Different, and this paper is not very long, and it's not particularly I think it's quite accessible. It's not a particularly technical paper, but the point of the paper is basically to describe the phenomenon of emergence, the idea that the whole can be more than the sum of its parts, and that really lies at the core of condensed matter physics. Yep. And so a more recent physicist, Robert Laughlin, also a Nobel laureate, he's famous for explaining or postulating a wave function which explains the physics of the fractional quantum Hall effect. So we can maybe talk about what the fractional quantum Hall effect is. It's an extremely fascinating effect in condensed matter physics. And he wrote a book called A Different Universe. So this book is sort of pop sci oriented. It's not oriented just at people in the field, but it's oriented to a broader audience. And I think he lays out some very interesting arguments for why we should understand emergent phenomena to be in some sense as fundamental to the functioning of the universe as we understand basic particle physics phenomena. So that being said, it certainly isn't the case that condensed matter has no pop sci. But what I think is the case is that, something like astronomy is sort of intuitively fascinating. You live your life under the night sky. Who wouldn't be fascinated to know about stars and black holes? And particle physics, in the 20th century for, various political reasons, particle physics is really was the frontier of physics research and funding for decades. And now that has sort of been slowly supplanted by quantum computing. So these types of topics get a lot of traction in the press and a lot of attention. But they really are kind of the tip of the iceberg. I mean, you think about a good example that I like to think about are, cold atom experiments, right? So cold atom experiments are experiments where you take atoms and you trap them using magnetic fields and light, and you can sort of treat them like quantum silly putty. You can shape these trapped cold atoms into all kinds of interesting arrangements. You can use them to emulate all kinds of phenomena. in condensed matter physics in other areas of quantum mechanics. There's a whole branch of condensed matter physics that I don't work on, but it's the branch of soft condensed matter physics. And so this is physics where the laws of classical mechanics are still operating. So we're not in the quantum realm anymore. But there are all kinds of interesting phenomena that sort of show up here. And, I think actually at some point it'd be really worthwhile to have some of the folks on from the department who work on that field, because I think people would be amazed how just within the scope of classical mechanics, there is still so much unresolved physics, and so much left to sort of wonder about. So yeah, I think those are areas that I'm sort of familiar with that I think people would find quite exciting, that maybe are not within the sort of mainstream.
Yeah, so Josh has a question. Can you elaborate on that? Emergent properties are fundamental. Sounds like an oxymoron. So I can give my take on this first, but I think James has a lot to say about this. So just from a perspective of sort of ETH, you see that you have an emergent phenomenon of entanglement sort of taking over, and that somehow emerges. You get statistical mechanics, and statistical mechanics is this amazing tool that we use every single day in physics, but you need lots of particles to sort of get there and use its power. But I guess I can definitely see what you're trying to say. Perhaps
I think Josh was bringing up a good point here, and I guess what I would encourage is for you to read it in Rob Laughlin's words. I don't know if I necessarily, I don't want to take a stance on the argument he makes in the book, and I don't necessarily know if I want to try to reproduce it. I think there is something semantic maybe about the claim, and I think that what Robert Laughlin is really responding to is a sort of what he perceives to be a sort of prevailing sentiment in the physics community about what the nature of fundamental science kind of looks like. And I would sort of encourage people to sort of read the book and take assess his sort of arguments and his discussion for themselves. I think maybe one thing that I can sort of try to comment on here is this idea that the whole point of the universe, on some level, the whole point of science. Let me
the whole point of the universe.
So let me maybe phrase that slightly less ostentatiously. The whole reason we can do science is because at each level of examination we have some fundamental independence from the levels below it.
Yeah.
I don't need to know about quarks to talk about how a baseball moves through the air.
Yeah. And
this really is the essence of emergence. This idea that we have what are sometimes called effective field theories in the business. And I actually know, John and I both know people who work on this topic. And the whole point is that emergentism is something that happens at a fundamental level in the universe, and that does not necessarily rely in obvious ways on the lower levels, the finer sort of levels of physical resolution. And so I think that's yeah.
And I guess I just want to add, I think it's very interesting, and somehow, it's sort of fundamental that the universe organizes itself in such a way that, the level number one somehow has emergent properties that produce level 2, and then I don't have to worry about level 1. And that is incredibly fascinating, and understanding that process is, I mean, on some level, a life goal for me.
I want to respond maybe to something in the chat if I could. I see that Marcin has asked why he was recommended you do this video. Marcin, maybe just for the company. I feel for you. I hope that your exam tomorrow goes well. I don't know if this is going to be the place to learn about the kind of stat mech that you're going to be tested on, but
if you need a quick and easy derivation of the ideal gas law, shout out to my video on that. Got some, there might be some good resources on the channel that sort of talk about concepts that you might be, I don't know, confused on, perhaps.
Definitely, if you want to learn about the origin of the Gibbs distribution, I would recommend you going and watching John's explanation of E.T. Jane's approach to understanding entropy and thermal distributions.
Yeah, absolutely. And, what is entropy? Giving it, sort of an intuitive understanding of that. Kevin Lambert says, So are you suggesting that emergence does not depend on the building blocks of the physical theory? Is it not all interconnected? It absolutely does depend on the building blocks, and that's something so fascinating, right? Like if you take the most exotic situation you could imagine, and that is an isolated quantum system, right? For some reason, when we look at Hamiltonians in nature, they give us Hamiltonians or ways that things interact with themselves in such a way that statistical mechanics is just given to you, right? And statistical mechanics is the one layer up where I can just sort of talk about the material as a bulk, even though there's lots of really interesting things going on there. But it's absolutely, it's the Hamiltonian that tells us how they interact, and it's sort of the steady states, the eigenstates of that Hamiltonian, like as explained in my videos, that sort of gives you these emergent properties where, the microstates, what's going on underneath the hood, tells you that you actually don't need to look underneath the hood for emergent properties.
I maybe want to, I want to add something to that as well. So let's go back to this. We spoke earlier in the chat about ice, and I think this is an endlessly wonderful example of a condensed matter system. So one thing that you might notice about a snowflake is that snowflakes tend to have what we call a six-fold symmetry, right? So snowflakes are in some sense patterned on hexagons. Mm-hmm. And the internal angle of a hexagon is 120 degrees, okay? But if I look at a water molecule, right, a water molecule on its own in isolation, I just look at one building block of an ice crystal. One water molecule on its own has a bend, it has an elbow, so it's got an oxygen sitting in the center, and then off the oxygen there are two hydrogens, and the water molecule is polar, so the oxygen has a higher affinity for the electrons. It pulls the electrons closer to it. So one side of the molecule is more negative, the other side is more positive. And this is the fact that allows water to build up into a crystal structure. But looking at the individual water molecule, you might say, okay, well, it's got a bend in it. Surely that bend is 120 degrees, right? I look at the building block. I understand that sort of bend in the water molecule is 120 degrees, and that's what gives me my hexagon. But oh, no. In fact, you measure what that angle is, and it's not 120 degrees. In fact, it's about 20 degrees less than 120 degrees. The fact that the hexagon forms out of many water molecules is a phenomenon that you can only understand by studying the interactions between water molecules and the way that they sort of correlate and come together. You can't just, obviously the physics that you're seeing absolutely is coming from the detailed physics of the molecule below. But just examining that wouldn't tell you that water is going to form a hexagon. In the same way, right, that if I look at the water molecule, I can say, okay, well, let me look inside the oxygen, right? Let me delve into the proton, right? And the proton is a composite particle made of what we call quarks. Quarks are sort of the building blocks of neutrons and of protons and of other forms of what's called hadrionic matter and mesonic particles. Studying the quark field, studying the details of what we call quantum chromodynamics, which is the field of the theory of how protons are put together, isn't going to tell you anything about how water molecules build up into an ice crystal. So we have this sort of segregation of energy scales. It's absolutely true that the oxygen wouldn't be there in the way that it is there without the sort of details of that underlying physics. But making predictions about how oxygen is going to behave not only doesn't depend on that underlying physics, but knowledge of that underlying physics doesn't even necessarily help you in making predictions about how the oxygen behaves. And so this is what we mean by a sort of segregation of energy scales, length scales, time scales over which these processes are happening.
Yeah, that was absolutely very, very well said. So Guitarman says, how long until someone writes a paper about memes as an emergent phenomenon? Can you model Reddit with the Ising model?
You know what, Guitar Man, I'm going to tell you right now, the people who work on the Ising model think that you can model anything with the Ising model. And there's a sense in which they're right.
Yeah, the whole world, the whole universe is well approximated by a free fermion model, if you ask me.
There's a theory, I think we're going to go a little far afield here, but why not, right? So some people in the chat might be familiar with John Archibald Wheeler. So John Archibald Wheeler was Richard Feynman's PhD supervisor, and he had this phrase, it from bit. And the essence of the phrase it from bit is that John Archibald Wheeler proposed an interpretation of the universe where, at the most fundamental level, the universe is based on information. So the universe can be broken down into basically yes/no questions, 1-0 questions. An Ising model, if you will. An Ising model is a series of, for those who aren't familiar, an Ising model is a very simple model of magnetism where you imagine a lattice, and on each of the vertices of the lattice, you have a degree of freedom that can be plus or minus 1, spin up or spin down. John has obviously talked about the Ising model, alluded to the Ising model, I'll say, in many of his videos, so his viewers will be familiar with that. And so you could maybe imagine, right, that if you really take this theory of nature seriously, if at the most fundamental level the universe is sort of a patchwork of ones and zeros, then maybe everything, including memes, can be modeled with an Ising model.
Perhaps. How complicated that might look.
Yeah.
Perhaps one day they'll have a straightforward way to map everything onto an Ising model. Wouldn't that be interesting?
The thing with the Ising model is that it is amazingly ubiquitous, and that it comes down again to a feature of this phenomenon of emergence, which something that sometimes I think we get backwards, right? On the one hand, we have symmetry, right? We have symmetries and we have dimensionality, and these are two features which we think of as really characterizing the universe around us. When we approach making a model in condensed matter physics, the thing that we really think about is what are the symmetries of the system that are relevant? What are the dimensions of the system that are relevant? We'll build the model based on sort of minimal assumptions about that. And it just so happens that the Ising model really does capture something extremely universal about all kinds of physical systems. The phase transition of a solid to a liquid can be captured by the Ising model. The phase transition that happens in a ferromagnet. If I take a fridge magnet and I heat up the fridge magnet, at some critical temperature, the fridge magnet will lose its magnetization, and before it melts, so it won't have melted, but it will have lost its magnetization. The Ising model sort of gives a sort of first order primitive account of how this happens. Maybe not the most accurate account, it's not perfect, but it gives an account of some of the salient features. And there are all kinds of other contexts where this model sort of arises. Deposition transformations. Maybe I have a sort of slab, a substrate, and I've got a sort of gas in the air that's going to sublimate as a solid and sort of cling to the surface. And I can imagine that at each point on the surface, I have a 1 or a 0. And that's an Ising model, right? So I can model sublimation onto a substrate with the Ising model. So the Ising model is pretty cool. It's pretty amazing how many things are actually...
Yeah, we'll have to do a video, or I'll have to do a video specifically dedicated to that. Also, I might be exposing my age here, but on the topic of memes, if you have some good condensed matter memes or statistical mechanics memes, you can email them to the email address listed on my YouTube account, and I'll put them on the slideshow here with credit, of course. I'll definitely credit the contributors, but
very good.
Get some diversity in the memes if you guys have any ideas. So Marcin says it's mainly for micro canonical and grand canonical ensembles. Yeah, absolutely. I very much wish you luck on your statistical physics exam. If you do like the ETH video, and I do appreciate that you that you've said that you liked it. Definitely check out the sort of the previous videos. I definitely check out a bunch of topics that are sort of glossed over in statistical mechanics courses that I think deserve a little bit more light to give you intuition about what's actually going on after your exam. Though don't learn information that is unneeded for your for your exam. 26 spins is literally so worth it. 26 spins is the most painful experience you will ever go through.
You do 26 spins on your
with a supercomputer. I could do 26 spins because it's about 100,000 by 100,000 matrix of doubles, and so I can do 24 locally, and I could do 26 if I had like double the amount of RAM. I think maybe, I don't know.
I want to emphasize to those in the chat not familiar with computational physics how much of a feat it is to implement enough symmetries to get 26 spins going dynamically.
Yeah, it's so you can get out to about 14 sort of naively. Then if you sort of insert a symmetry called like magnetization, like depending on the symmetries depend on the model, of course, but if you insert magnetization symmetry, you can get up to like maybe 16, maybe you could do 18 comfortably if you're really good, and then translation invariance gets you out to 20. And keep in mind, every single time I insert a symmetry, it sort of doubles the amount of code that you have to write. And so then you insert, you can do a spin flip symmetry and sort of a spatial reflection symmetry, and that gets you up to about 24. So each time you insert a symmetry, you basically get 2 more spins for an exponentially larger amount of effort and code and tears and frustration and debugging. But it's a good time. Once you're done, it's a good time. So, oh, sorry.
Yeah, go ahead.
I was going to say, Josh, and just to do a shout out, eventually we're going to do a video on this, but there's definitely very clever computational methods that are approximations that you can go into. James does quantum Monte Carlo simulations. There's a number of ways you can do these, and those are very clever and very interesting. And there's tensor network algorithms that are very interesting. That it turns out you don't need all these numbers to effectively simulate a lot of things. But if you want to do it to absolute precision, you need everything all at once to do it exactly, and then that's just extremely, extremely difficult. Josh says any system you can more or less cast in terms of two levels is a pretty good fit for the Ising. Yeah.
Yeah, I think that's I think that there's a sense in which that's absolutely right. In fact, you can even go farther than that, right? So beyond the Ising model, there are the so-called POTS models, and the POTS models sort of generalize the Ising model to a case where you have, an n-level system sitting on each degree of freedom. Each degree of freedom can take n values.
Well, I guess you'd have to be careful. Like in the quantum regime, you could have like a Heisenberg-like interaction that is certainly.
That would, I guess I would characterize, I would say if you had a Heisenberg interaction, you're sort of, I think what we need to be careful with here is this word two-level system.
Yes.
So the individual degrees of freedom, if each say particle in your system can only assume one of two values.
Yes, then I agree. But once you insert quantum mechanics and you let these spins just sort of do whatever they want, then
right, like you might be tempted to think of a spin system as a two-level system generically, but in fact, like you're saying, if you have a sort of generic interaction between two spins, then even though the spins can only assume one of two values, the Ising model no longer becomes useful for explaining the physics that arises, say like you say in the case of a Heisenberg exchange or an XY exchange or some of these more exotic kinds of spin interactions that you can get in a material.
Hey, what's going on, Chris? Chris is a really good friend of mine from undergrad, and he trolls me daily by viewing all of my papers on ResearchGate, so that ResearchGate spam emails me saying researchers are viewing my papers. I'm always so excited. I'm like, oh, who's looking at my stuff?
Very good.
Very good. Very good. Okay, so there's not a lot of chat going on here. So perhaps we can start talking about, sort of the topics from the last two videos. I gotta read them all, baby. Yeah, I definitely appreciate that at least my friends are reading my research papers.
That's what we do. We do it for the people we love. That's who we make physics for.
Absolutely.
With all of these other goals of, we make physics for the people around us.
Absolutely. Okay, so let's jump into some of these Reddit comments. Of course, if you go on Reddit, I answer all these comments pretty thoroughly in the thread, but perhaps James might have some extra takes on it, or I might have some extra things to say. Yeah. No, it's fine, Josh. It was an interesting idea to sort of hop off on, and
I think an important point to emphasize, it's not just spins; it's anything that can sort of be
sort of classically two different states.
Yeah, classically, essentially.
Yeah. So someone on the Reddit thread, Mar1203, said that ETH is surprisingly simple, and I definitely agree with that statement. It's sort of like, it is a very simple statement. You don't need a lot of physical, you don't need a lot of physics background to sort of appreciate it. So I guess an interesting question to ask you is, do you think that how simple the eigenstate thermalization hypothesis is, or the actual statements of the of ETH, do you find those things to be surprising, or do you find them to be intuitive? And sort of, I know it's tempting to answer the question from the perspective of like, you already know ETH, I've already argued with you and got you on board with ETH over the past few years, but like try to like channel that inner James that didn't know what ETH was.
Yeah, right. So I think on principle we should never be surprised. I want to say something quite bold, like, the whole point is to figure out what's going on.
Yep.
Right. And why do we have statistical mechanics? How is statistical mechanics consistent with classical mechanics? I think ETH offers, I think, a very compelling explanation for this. So even before we'd met, and I didn't know anything about ETH before I met John. But even in spite of this fact, the sort of building blocks of ETH I was familiar with from the measurement problem, right? So there's this sort of problem in quantum mechanics, which is that the Schrodinger equation, which tells you how the universe evolves in time, has a specific property called unitarity. And unitarity is basically just the property that if I start out with a state that has a particular normalization to it, that normalization will be preserved by time evolution. So remembering that a state is essentially a probability distribution, or can be turned into a probability distribution. Probability distributions, if I add up all the possible outcomes, have to sum to one. If I take a coin and I ask, what's the probability of heads plus the probability of tails, I have to get one, because one of those things is going to happen. And so unitarity just ensures that this is true. But I'm going to say tentatively, the heuristic rule for how we compute measurements in quantum mechanics, the Born rule, which some interpretations of quantum mechanics argue is actually not heuristic at all, but in fact the most fundamental part of the theory. People like Christopher Fuchs, who studied quantum Bayesianism, would sort of make this claim, I think. Not to put words in anyone's mouth. I don't know Christopher Fuchs personally. I don't even know if I'm saying his last name correctly, actually. But in any case, measurement processes are not unitary. And so there's a question, which is, how is it that the measurement process, as described by quantum mechanics, can be made consistent with the fact that the Schrodinger equation is unitary? And the way that people tend to think about this problem, or one of the ways that this problem is thought about, and this is not my area of expertise, but this is how I sort of got exposed to these ETH type ideas. One of the ways you can think about this problem is that your quantum system and your measurement device are both quantum mechanical. And so you have to understand that when the quantum system, you have to think about the joint system. You've got the state that you're measuring, and you've got the measurement device that's doing the measurement. And as time goes on, those two things are going to become entangled. The process of measurement is the process of entangling your system with the measurement device. And the consequence of this is that the state after the measurement does not look pure anymore. It doesn't look like a pure quantum state, because I've traced out the part of the system that is concerned with the measurement device. And I've been left with the remainder, which is now the entangled subsystem of the state. And so this is one way that you can sort of try to approach getting this non-unitary behavior in your state side in the state sector of the system, or of the joint system and measuring device, I should say more precisely. So the fact that in ETH we are leveraging this fact to attain local thermal behavior was not so surprising. That seemed quite natural to me, because the whole point is that, and this is actually something that I think a lot of people have there's a bit of a misconception about this. You think about thermal behavior as being really the polar opposite of quantum entanglement, and there's a sense in which that's absolutely true. If I have a state, and that state is in a quantum entangled arrangement, and I allow that state to interact with an environment, the process that will occur is a process called decoherence, where the environment will act on the system so as to reduce the amount of entanglement in the system and make the system look effectively thermal. But how is that happening? The way that is happening is that the state is entangling with the environment itself.
Yep.
So it's not that entanglement is disappearing so much as it is that entanglement is moving or growing, or sort of assimilating the system and its environment, or the system and its measurement device.
Yeah, I guess to
So
turn it back into the language of the video, like that, like the entanglement entropy, the reduced density matrix, and ending up looking thermal for that initially, subsystem that starts in an entangled state. Like you still have a very large entanglement entropy sort of after or sorry, no, that's perhaps the wrong way to say it. The entanglement, basically it's the same story as before, right? Like you just have an isolated quantum system, and the subsystem that's not initially entangled entangles, and like that grows this bipartite entanglement. So it's extremely natural that this all of this language sort of fits together.
definitely.
Sorry, I interrupted you there. Keep going on your.
Oh no, no. I think that's an important interjection. I think to sort of normalize the way the language that we're using here to discuss this. Yeah. So from that point of view, I think ETH is quite intuitive. Now, the fact that excited states in the spectrum have a volume law, I think also shouldn't be too surprising to us. Because even if we don't think about ETH, even if we sort of imagine a quantum system that is in equilibrium with a thermal bath, we understand this idea that classical entropy goes like a volume law.
Yep.
And so, it's sort of natural to us to imagine that that this is happening. Excited states and there are different ways of picturing this, but one of the ways that we tend to study, maybe I'll come at the question from a sort of condensed matter side. So one of the ways that we study condensed matter systems is we try to figure out what the ground state is doing.
Yep.
And the ground state sort of acts like a musical instrument. It can play sort of specific notes, and in other words, it can sort of vibrate and oscillate in sort of characteristic ways, characteristic of the pattern of organization that the material is assuming. And we can conceptualize those notes, those we call them excitations from the ground state, as being sort of like particles. So an excitation is like as if I had the ground state, which is like the vacuum of a little universe, and an excitation, a sort of vibration in that ground state, is like a little particle that's moving through it. So what you could imagine, right, is that these particles sort of carry information about one part of a system to another part of a system. And as I increase the temperature, as I go up to more and more excited eigenstates, insofar as this picture can be extended to those states, if I go to higher and higher states, I can imagine a proliferation of these quasi-particles, of these sort of pseudo-particles that are flying around my system, carrying information all over the place, which make each sort of little local subsystem look like a total mess. It just looks like a totally thermal random mess because of this, sort of quasi-particle picture. So that's one sort of way that, from a condensed matter perspective, again, ETH really is sort of comfortably intuitive. The idea that the subsystems of an eigenstate should scale, or should have a sort of volume law scaling in their entropy, should be very entangled with the other subsystems, sort of follows in a very satisfying way from this picture.
So I guess the interesting question that I would have here then is like, for me, like there is something at least a little bit surprising about the fact that the mechanism to recover stat mech in these situations is the structure of the eigenstates. Like, did you think that this? I guess when you put it all all the way back like that and all these abstractions and thinking about it this way. Like that definitely makes sense to me. Like if you think really, if you really come at it from that perspective, but like if you came at it from like sort of a naive perspective, and then you looked at the infinite time average as we did in the first video on ETH, I guess you might imagine that there might not be a simple mechanism to make the infinite time average equal, say, a microcanonical average, right? Like it is surprising
Sure.
that the mechanism does come from the eigenstates rather than, I don't know, perhaps the probabilities, like the way your probabilities are populated when your system size gets very large or something like this.
Right. Yeah, I think that's I think this is there's a sort of intimate link between dynamics and thermodynamics, an intimate formal link, a mathematical link, which is that the Gibbs state, the sort of thermodynamic equilibrium state, looks like okay. So let me sort of set something up here. So if I ask myself, what does the density matrix, if you've watched John's video, you know what the density matrix is. The density matrix is the thing that sort of contains all your information about the state. If I look at the density matrix that corresponds to the thermal average,
Yep.
it is in fact the imaginary time of what, if you look at the operator that takes care of the evolution of the state in time, and you rotate it from real time into imaginary time, you get that thermal state. So there's this kind of intimate link between thermodynamics and dynamics that we actually exploit all the time in calculations.
That's fair.
You can look at equilibrium thermodynamic properties of a system, and you can infer from those things about the dynamical response of the system to an external perturbation. And so, and I think there's a sense in which we don't really fully understand why that is. If you read Piers Coleman, who a physicist at Rutgers, has a very good many-body physics textbook that I think is really swell. And in the book, he sort of mentions that this was something that even Feynman, throughout his life, tried to come up with some intuitive explanation for and really just couldn't. This relationship in imaginary time and real time between temperature and time is something that I think could, maybe it's sort of in some sense coincidental, but it certainly is so useful and so natural that one would maybe expect a kind of intuitive explanation for it. And I don't know. So that's sort of maybe an interesting fact about thermodynamics. I maybe want to respond to.
So let's so Gabriella, absolutely. Next time, I haven't set that up for the stream yet. I'll have to set up some window to show the Reddit thread, but I agree that that's a great idea. 26 spins is also my favorite meme because it sounds like, to me it's such a feat, but I think to an outsider that sounds so pitiful. Okay, so Kevin Lambert said, could you expand on what you mean by the process of measurement of the state?
Sure. So in a quantum system, quantum mechanics is set up a little differently from classical mechanics, right? In classical mechanics, we don't worry so much about the process of measurement because in classical mechanics, we assume that we can make a measurement of a system. Say I can measure the pressure of a balloon without changing the pressure of the balloon substantially. So I can extract information about a system without disturbing it. But in quantum mechanics, that's not true. In quantum mechanics, when I measure a system, I'm actually disturbing the system. And so the process of measurement in and of itself induces some uncertainty. So an example of what I mean by measuring the state is, imagine I have an oven. And this is a very famous experiment. It's an experiment that you learn, maybe if you're those watching who have done an undergrad in physics will be familiar with the experiment. Imagine I have an oven and I have silver in the oven, and I've heated the oven up so much that the silver is now a gas, and the gas is allowed to escape through a small hole. And I take the escaping gas and I direct it into an inhomogeneous magnetic field, what we now call a Stern-Gerlach device, named after the first two people who did this experiment.
This is my favorite quantum mechanic. I definitely want to make a video. Like, once I get, skills that are better than latexing up a PowerPoint slide, that's definitely something...
It's one of the classics, isn't it? It really is one of the all-time classic physics experiments. And so what you find in this experiment is that the silver atoms have a spin. They have a magnetic moment, a small magnetic moment that can be up or down. And what the Stern-Gerlach experiment establishes is that there is no intermediate value of spin. The spins are either up or they're down. They're not anything in between. And the way that this is established is by passing the silver atoms through this inhomogeneous magnetic field and then placing a screen behind the device so that the silver atoms make a mark on the screen when they hit it. Now, if the spin of the silver atom is co-aligned with the field, parallel to the field, it will deflect in one direction, and if it's anti-aligned, it will deflect in the opposite direction. And so what you would expect, if the value of the spin could take any possible value, you'd expect the screen to sort of present with a smudge. You'd expect a sort of uniform distribution of silver atoms on the screen. But what you in fact see is two distinct bands of silver atoms, one corresponding to the upspins and one corresponding to the downspins. So in this context, the state that we're talking about would be the thermal state of the silver atoms coming out of the oven. And the measurement process would be the process of putting them through this Stern-Gerlach device.
So do you Josh says, if that's what you're reading, Josh says, do you think that temperature/imaginary time correspondence relates to entropy as the arrow of time? I guess I definitely haven't thought about that a lot myself, so I'll definitely
I have some strong opinions about this. It's going to shock you to know.
Shocking.
It's going to shock you to hear, John. I have strong opinions about this question. So that's a great question. And so for those people who maybe are not so familiar with this, maybe a slight bit of background, right? A big question that we ask in physics that is super hard to answer. It goes back a very long time. Is why does time go forward? Why is the future different from the past? It seems like the most obvious thing ever, right? But I can remember the past. I can't remember the future. Time seems to go inexorably in one direction. And that question becomes even more pertinent when you learn about our theory of gravity, the theory of general relativity, because what this theory shows us is that there's a sense in which space and time are actually sort of two parts of the same whole. There's a sense in which space and time sort of exist on equal footing.
Yeah.
And so, why is time so special, right? Why am I sort of being dragged along the time axis? And one of the ways in which people cash this out is by saying something like, well, entropy also tends to increase as time goes on. So, you could imagine that if I take all of the air in this room and I cluster it into the corner of the room, as time goes on, the molecules will bounce off of each other and off of the walls, and eventually the molecules will sort of be evenly distributed throughout the room. And so in that sense, the sort of entropy has increased because there are many, many more ways to distribute the molecules throughout the room than there are to distribute them sort of clustered in the corner.
Yep.
And so people say, well, that's what the flow of time is. So there's a sort of claim that exists out there that says something like the reason time goes forward is because the universe is constantly sort of under the laws of classical or quantum mechanics, colliding with itself, bouncing off of itself, and arriving at more probable states. And the more probable states are, almost by definition, precisely those states which correspond to a greater number of possible microscopic arrangements. And so this is the reason that time looks like it's going forward.
So just to interject here, I just don't see how that satisfies the question. That just seems like you're explaining what's happening without answering the question.
Yeah, and I think that that's a good point. And I think one of the things about this question that's so devilish. I should say one other thing about one of the reasons that this question is so devilish, which is that if you look at the say Newton's laws, right? So Newton's second law is the prescription which tells you how to calculate the position and the momentum of a particle in response to an external force. And what you'll notice in this equation, for those who are maybe math aficionados to say it technically, is that it relies on the second derivative with respect to time. It relates the acceleration to the force. And so what this means is that there's a sort of manifest time reversal invariance. If I put time in the other direction, the microscopic laws of nature, Newton's laws, look like they're the exact same.
Yeah.
So Newton's laws don't care, forward or backward doesn't make a difference. And so why is it that on the aggregate, the universe looks like it's moving forward? Why is there this symmetry breaking? And I think the only reason why I think it's a bit tricky, and I'm not in philosophy of science, and I think that there are people out there who are better suited to answer this question than I am. But I think the reason that it's tricky to say this business of, well, entropy is the error of time, is because there's something that's a bit of a tautology about it, isn't there? We're sort of saying, well, entropy increases as time increases, and the fact that entropy increases as time increases is the reason the past looks different from the future. But it's like you're already starting from this claim that time is increasing.
Yeah.
So how are we talking about, just talking about time increasing is sort of setting the preferred direction of time's flow. So there's a sense in which maybe this question is but I don't know. I mean, maybe that's not the most rigorous criticism of the entropy as the error of time question. And I certainly think that there is merit to what Josh is asking here, which is that this relationship between the sort of thermodynamics of a system and the sort of time evolution of the system, does that have something to do with the connection between entropy and the flow of time itself? I mean, Indeed, maybe. Certainly from the point of view that, if you take any system, okay, so there's a whole sort of world of foundations of StatMech that at some point, John, we got to have a philosopher of science on here to talk about some of these things, because I think there are so many interesting questions here. But one interesting question is that if I take a system at equilibrium, the whole point of the fact that it's at equilibrium is that I can't tell where it started.
Yes.
So I start a system in one configuration, I start a system in another configuration, I let time run for a long enough period of time, and I arrive at the equilibrium configuration, and the equilibrium configuration, the whole point is that I can't rewind it. I can't go backwards from it.
Yeah, so for those of you who were potentially at the last stream or have watched the last stream, this is a process known as scrambling, and it's a very interesting, active area of research where you're losing memory of your initial conditions because your macroscopic information ties you to lots and lots of different initial conditions that tell you that your equilibrium state should be identical to all of these situations that are radically different than where you started, which is very, very fascinating. Time eventually sort of erases your fine structure that you started with.
Yeah, absolutely right. And this is a real problem. Like, this is a deep problem in the philosophy of statistical mechanics, because classical mechanics doesn't work like that. Like, the classical mechanics that you learn as a student are, the whole point is that I can always unwind classical mechanics. I can go back to any point. Temperature goes to derivative of entropy with respect to internal energy.
Not to my knowledge, but that would be very interesting if there was. Time goes to I times temperature goes to I divided by derivative of entropy with respect to internal energy. I guess that would be a very profound statement, and I guess I would be very. I'm always very skeptical of arguments that sort of start with thermodynamic definitions. I don't think that that's perhaps the way to go here, but perhaps it is. Perhaps it is.
Perhaps it is that simple. Perhaps it is really as simple as what. I think that there is a compelling point that Josh is making here. Like, I think that this connection is definitely one that warrants some investigation. And people do talk about this problem from time to time. There's a kind of radical argument out there. Maybe it's not so radical, but I think it's pretty cool. There's a researcher at McMaster who's published some work on this topic, and there are others. So one of the problems, right, is that in quantum mechanics, time and space are no longer treated on equal footing. In particular, in the sort of standard formulation of quantum mechanics, position is treated as an operator, time as a parameter. And there are ways of getting around this. So there are actually sort of extensions of quantum mechanics that upgrade time to the status of an operator, or attempt to upgrade time to the status of an operator. And then there's the sort of theory that we use in particle physics, quantum field theory. Quantum field theory is not just one theory. It's a sort of methodology of constructing theories. And in quantum field theories, you demote position to be a parameter so that you can talk about time and space on equal footing, and therefore bring relativity, try to join relativity to the ideas of quantum mechanics. And there's a sense in which maybe that whole line of reasoning is a bit esoteric to our place in the universe. There are arguments out there that say something like, well, if we take quantum mechanics really seriously as the foundation of everything, then maybe we should imagine that things like space and time themselves are emergent properties of quantum correlations, quantum entanglement between whatever the sort of fundamental elements of the universe are. So there's a sort of long tradition of this work in mainstream sort of high energy physics. And more recently, there's this work by Stephen Wolfram, who's a British particle physicist, founder of Wolfram Alpha, programmer of Mathematica. And in Wolfram's formulation, it's kind of a I think the best way to characterize what Stephen Wolfram is doing is as a kind of numerical scheme. He's basically saying, well, let's imagine that we have graphs, and we have simple rules that take as an input a graph and take as an output another graph. And what we can do is sort of choose these rules in a way that is sort of strategic and interpret the graphs in a certain way so that the graphs actually look like they are giving us back the physics of electrons and quantum mechanics and relativity and so on. And so this formulation, I think, is kind of compelling because it shows us that maybe starting out with a notion of space and time is a bit wrong. Like, maybe we shouldn't be starting out with the idea that space and time are the fundamental elements of reality. Maybe the fundamental elements of reality are something deeper, more abstract than that, from which space and time then emerge. And so that's sort of maybe an interesting This
That's
is
an
all
interesting take.
This is all very kind of
It's very speculative and very early.
very out there, yeah.
Early
but,
on,
kind of interesting.
But it would be really cool if it sort of reduced to this equation that Josh alludes to below. If somehow after all these complicated arguments, you get something out that is as sort of straightforward, but it works out very nicely.
Sure.
With what Josh has been writing here, but so the stream was planned for an hour, guys, and I think we're gonna cut it short here. We might be able to do a longer one in the future, but it's Mother's Day. I do have plans. So I appreciate everyone who came out. It was really nice hearing from you guys. If you do have any tips for the next stream that you'd like to see, or any other criticisms or anything, or you want to peer pressure James into coming back on the show next week or something like that, definitely let us know in the comments. Again, appreciate all the viewership. Definitely have a great night. See you guys next time.
Thanks for having me on. Look forward to next video.
Yep. See you guys. Oh, that went really well. You did awesome, dude.